It just started, yes. Okay, let's get started. So we have these related rate problems that we're working on, and then in a week or so, we're going to start working on what's called optimization problems. It's another type of kind of real-world application, like word problems. Okay, and so my experience is that this is kind of a challenging part of the course, and then lots of those questions involve trig. So I want to give you a half-an-hour crash course in trig because you're going to have you're going to have a related rates set 2 for the weekend, and many more of those involve trig, and then these optimization problems, lots of those have trig. So this is, we're going to get right to the heart of it in 30 minutes, and so here's where it all begins. Trig begins with a circle, and I'm showing you the radius there with that purple bar, and so what I'm going to do is I'm going to take that radius, I'm going to peel it off its normal place, and wrap it on the circle, maintaining its length of 1 radius. Okay, did you see that? See it again. Ready? So there it is where you're used to seeing it. We're going to maintain its length and wrap it on the circle. Maintain its length. So that still is 1 radius length. Hear me now. The basics of trig is about measuring lengths with the radius. That's what trig is about. Measuring different lengths using the radius as your measuring stick. Okay? So let's see how this works. So let's talk about angle. So I'm going to sweep out an angle here from the positive x-axis, and we're going to sweep counterclockwise from the positive x-axis, like this. So this angle right here, the measure of this angle, measured by 1 radius length, is 1, because the arc length is 1 radius length. Okay, and we can measure. So I'm just gonna put it here. And we want to measure other lengths as well in terms of the radius length. That's what that's the basics of trig, is about measuring lengths, different types of lengths, using the radius, okay? So here's some more length. So in that diagram, where does the radius length show up? It shows up in many places. In fact, so just looking here in the upper right-hand quadrant, I see 4 places where we could label, this is a radius length. So looking in that upper left quadrant, there are 4 places we could say, this is 1 radius length. Can you find all 4? See if you can do it with the person next to you. In the upper right-hand quadrant, four different lengths that are all 1 radius length. Okay, let's see how you did. Here they are. Ready? From here to here. Did you find that one? Okay, that's one of them. All right, from here to here. That's one. That's a radius length. Okay, this arc length that I showed you originally up to that tick mark right there, that's 1 radius length like I initially showed you. And where's the last one?
The hypotenuse of the triangle.
This is a This is a radius length from there to there. Did you find all four? Okay, now I'm going to call that, or let's say, so now here's what I want you to do. I want you to estimate. I've got a purple arc. I've got a blue segment right here. And then the red segment. So the purple length is arc length, okay? The red segment is the vertical distance above the horizontal diameter. Do you see that? And then the blue one is the horizontal distance to the right. And they're all referencing in relation to this point right here. So I've got this arc length that gives me a point on the circle. And so now for that point on the circle, this red segment is its vertical distance above the horizontal diameter. This blue distance is the horizontal distance to the right of the vertical diameter. And then that whole thing is the arc length. So I want you to estimate using arc length as the unit, or using the radius as the unit of measure. I want you to estimate those three lengths. Okay? So you're going to estimate, so the total length of the purple arc, estimate it using the radius as the measuring stick. Estimate that using radius as the measuring stick, and estimate that. Go. Does it make sense?
Oh, you're using the
Okay, let's see how you did. So that purple arc length, if you were to measure that using the radius as its measuring stick, what would you estimate, just an estimate for?
Oh, it's 40 centimeters.
No, forget 40 centimeters. Forget 40 centimeters. You're measuring these lengths using the radius as the measuring stick of the length. So that purple arc, what do you estimate that length is using the radius as the measuring stick? Okay, no, it has nothing. Forget 40 centimeters, please. I never said anything about 40 centimeters. Turn it off. Okay, here we go. You're measuring these lengths using the radius as the measuring stick. So how long is that arc length in terms of the radius? About what? Matt, go ahead.
1.35 radius.
Okay, so yeah, it's like 1 and a little bit more. I put 1 1/4. If you had 1 1/4, 1.25, that's a decent. Does it make sense?
Yeah.
Let's try 16. Okay. How about the vertical distance, the red distance above the horizontal diameter measured in using the radius as a measuring stick? What did you estimate that to be? What's that? 0.9. What do you think about 0.9?
Probably 0.9. A
little more than 0.9. Okay, yeah, that's the ballpark though. 0.9. It's almost 1 radius length. So like 90% of a radius length. How about the horizontal distance to the right?
Probably about a quarter. 0.25.
A quarter, something like that. So what did I say? Yeah, I said a quarter also. Oh, jeez. Okay? Do these numbers make sense? This is the heart of trig. And we'll get to the semantics in a second, but measuring the arc length using the radius. So the way I've got it set up now is about 1 1/4 radius. And then the red vertical distance to that point on the circle, about 0.9 of a radius, and the horizontal distance is about 1/4. Okay, now I'm going to tell you that the radius is 40 centimeters. And I'm also going to give you the actual arc length in centimeters. Okay, that actual arc length is 52. That actual red length is 38.4. And that actual blue length is 10.8. Now I want you to compute exactly how many radius lengths each of these lengths are. Compute exactly, given the information, the new information, exactly how many radius lengths is the purple, exactly how many radius lengths is the red, and exactly how many radius lengths is the blue segment. Go.
But then we have 52 values. Wait, there we go. There's our three. What formula are you using?
I'm using like 15 by 40.
Okay, so how about the arc length? The exact length of that arc measured in the radius.
1.3.
People are saying 1.3. And how did you get that?
52 divided by 40.
Ah, sorry. 52 divided by 40. And what does a quotient mean? 52 divided by 40. What did we say that meant? Relative size. So when everything's relative to the length of the radius. So if you want the length of that arc relative to the radius, you use a quotient. 52 40ths, or 1.3 radius lengths. Okay? And what did you get for that red segment, the vertical distance above the horizontal diameter?
0.96.
0.96. Stop looking on that. Click down here. Okay, so what is that? That's the length of that relative to the radius. The length of that red stick relative to the radius, or measuring that length with the radius, 0.96 radii. And the last one?
0.27.
0.27.
So basically it's pretty straightforward.
Okay, so makes sense so far. So this number, 1.3, which is the relative size of the arc length to the radius, does anybody know what that is? What we call that, 1.3 in this case. Okay? That is the angle measure. Theta. Angle measure is the relative length of the arc to the radius. The length of the arc relative to the radius. That's where we get the angle measure in radians. Okay? And then what about this? This number, 0.96. So that vertical distance to the point on the circle relative to the radius. Anybody know what we call that? Please, someone in my sine. This is sine of theta. Given an angle theta, a relative arc length, whatever your vertical distance is to that point, measured in the length of the radius, that's sine.
last one, I believe, is
So now this length measured in the units of the radius is
cosine.
cosine. So these are the three basic quantities, the three fundamental quantities in trig: angle measure, sine of theta, and cosine of theta. And they're all measuring a length with the radius, all of them. First one, angle measure. That's measuring the arc length with the radius.
Yes.
Sine theta, that's measuring vertical distance with the radius. And then cosine theta is measuring horizontal distance with the radius. Okay, so what's the greatest possible value sine theta could take on? If we're talking about points on the circle and their vertical height measured in radius lengths. 1 at the top. It can't be greater than 1. And what's the least value it could have?
Negative
1
1.
at the bottom of the circle. Because if it's a measurement in radius length of a point on the circle, you can't get any further away than 1 radius length, and that's at the very top of the circle. Same with cosine theta. Where does cosine theta have its maximum value?
1. Right there.
When the angle is 0. When the arc length is 0, we start there on the x-axis. There's where cosine theta has its maximum value, which is 1 full radius length. Every other value will be less than that. Okay, let's try it again. Okay, now the radius is 0.2 miles. So the radius is 0.2 miles. I want you to estimate the value of theta, sine theta, and cosine theta. So that's this first thing, first box in each. So you're gonna do this. Estimate the value of theta, estimate the value of sine theta, estimate the value of cosine theta. Now the radius of the circle is 0.2 miles instead of 40 centimeters. Go, find your estimates. Okay, if you're tracking, what are these estimates? Same as the before, because it doesn't matter how we're measuring the radius in terms of miles or centimeters. We're still measuring this arc length in terms of the radius. So our estimate is 1.25. And our estimate for sine? 0.9, 0.95.
0.95.
And then for the estimate of that blue segment, the horizontal distance in terms of the radii.
0.25.
Yeah, 0.25. So it doesn't matter what your radius of the circle is, if it's big or small or galactical or microscopic. These values are always relative to the radius, and so if I don't change the position of this point, if I don't give you a new arc length to start with, then we're going to have the same estimates for arc length in terms of the radius, vertical height in terms of the radius, and horizontal distance in terms of the radius. So now the radius is 0.2, and I'm going to give you these. So that arc length is 0.26 miles. And I'll make this all a little bigger. There we go. Okay, go. So now find the exact values of these in terms of radius length. So if the radius is 0.2 miles, and these are the exact distances in miles, compute the values of theta, sine theta, and cosine theta exactly.
Aren't those answers in there the exact ones, actually?
What's that?
Are those answers in given units the exact ones?
These?
Yeah.
Yeah, these are exact, and the radius is exactly 0.2 miles.
Yeah, that's what I got.
So what'd you get?
I got the same answers.
Okay, so it's the same because I didn't move this point. So even with this much, much bigger circle from 40 centimeters to 0.2 miles, the arc length relative to the radius is the same, the vertical distance relative to the radius is the same, and the horizontal distance relative to the radius is the same. And that's what the angle measure and sine and cosine are about. So how can we get different values? Well, I have to change
the ratio.
Yeah. Okay, so now I want you to estimate theta, sine theta, and cosine theta. So estimate theta, sine theta, and cosine theta. For this point, okay, so it's the arc length from here, starting here, ending here. So let me, there we go. You're estimating theta, sine theta, and cosine theta.
The radius is still 0.2 miles, right?
Okay. Sure.
Okay.
Oh no, sorry, it's 40 centimeters.
4 centimeters.
Okay. Oh, sorry, I mean it's 3 feet.
3 feet.
The radius is 3 feet now.
So it's a yard. 3 feet is 1 yard, right?
No, the radius is 100 yards.
Are you going to keep changing it?
Doesn't matter.
Because it really doesn't matter.
Right,
The radius
right.
will still be the same.
Okay, what do you estimate theta to be?
Maybe.
As an estimate. Oh, sorry, but I need to show you where 1 is, right? So that's where 1 ends. That's 1. 0.5 about. A half. Okay? So then what we're saying then is now we're estimating sine of 1/2. By estimating sine of theta, we're estimating sine of 1/2. So sine is a function that takes the arc length measured in the radius, or the angle measure, and then gives you the distance of the red line. Estimate. So estimate for sine of 1/2. Just a little bit less than 1/2. Do you see that?
Probably maybe 0.47, 0.48, something like that.
So yeah, we probably can't know to that degree, but a little bit less than a half, maybe 0.45. Okay? And now we're saying what is cosine of 1/2? About what?
0.85.
Yeah, so it's more than 0.8 because that'd be 4/5, and it's not quite 9/10 or 0.9, so maybe 0.85 in this case. Okay, questions on that example? Okay, so let's let the radius be any radius, and it can be any unit, anything you want. So we'll just say feet, okay? There's r in feet. We'll call the blue segment x in feet. And we'll call the red segment y in feet.
So it could be like 7 feet.
7 feet, 100 feet, 100 miles, whatever you want. But we'll just call it r, x, and y. So now what I want you to do is I want you to express, this is going to get really cool in a second here, if it hasn't already. Express vertical distance in radii in 2 ways. You've got, everything I've showed you so far, now you've got 2 ways to express the length of that red segment in radii. You have 2 ways to express that now. Okay, if this is our angle measure theta, say. Okay, and same thing, horizontal distance. In the units of the radius. You've got 2 ways to do that now. Go, see if you can do it. So you're going to express the length of that red segment in 2 different ways. Express the length of the blue segment in 2 different ways. See if you can do it. Go. I want to see what you guys have. I don't know anything about pi over 4, 3 pi over 4. Only what we've done in class today.
Yes.
So that, how would you measure that vertical distance in radii? Using the length of the radius. Don't use the estimates. These are all exact now. All exact. Okay, so did all this stuff on the spreadsheet make sense? How did you get the value, the exact value of, say, the vertical distance above the horizontal diameter? What did you do?
Y over R.
You took that distance in this case miles, and you divided it by how many miles the radius was. Okay, so how would we write that generically then for this case? Y divided by R, right?
Yep.
Doesn't that compute how long Y is in the units of R? And we estimated that ratio to be about 0.45, but Y over R is exact. How else can you express that length, that vertical distance in radii?
Square root of x squared minus
It's the square root of r squared minus x squared.
Okay, that's true, I guess.
Pythagorean theorem.
Also, sine theta. That's what we defined it as, right? Sine theta is this vertical distance measured in radii.
That's what I told you first.
Horizontal distance in radii. So how do we measure that in terms of the radius? X over R and cosine theta. So these are both exact versions of measuring first the red segment. Okay, so just whisper. If you're talking about math, that's great. Just whisper. So measuring this thing in terms of the radius, y over r. It's the relative size of that to the radius. And we define that. That's how we define sine. That's what sine is. And then same with cosine. It's the relative size of that horizontal distance to this point relative to the radius, x over r. And that's going to be end up being a fraction of the radius. Like we estimated this to be 0.45. Okay, whisper. Please whisper. And then we estimated this to be about 0.85. Okay, now watch. So we see a right triangle there. We call this side the hypotenuse. And so the red segment is across from or opposite our angle. So we call this the opposite side.
And the x would be the adjacent.
And so this leg is next to, so this is the adjacent leg. So taking y over r is the same thing as taking opposite over hypotenuse. So what does that ratio mean? Opposite over hypotenuse. It's a relative size of that height of that leg to the radius. Or measuring that vertical height. And then cosine would be adjacent over hypotenuse because it's measuring that length relative to the radius. That's where these come from. They come from measuring the vertical height to the point on the circle relative to the radius, and measuring the horizontal distance to the point on the circle relative to the radius. Because the radius becomes the hypotenuse of the right triangle. Okay, then there's another one.
Tangent.
If we were to draw a tangent line over here, like this, and took the length to the ray, right, from there to there, and measure that in terms of the radius. See, it's all about measuring to the. If we measured that length in terms of the radius, it would be the same ratio as our red stick to our blue stick.
Opposite over adjacent.
And that's why it's opposite over adjacent. But it's still a value that's measuring a length, in this case, the length along the vertical tangent, in terms of the radius. You're measuring this thing in radius lengths. And that's why this is the tangent line. That's why it's called the tangent function.
So it'd be y over x in this case?
Yeah.
Okay.
Okay, so that is our crash course in trig. How'd we do? Oh, sorry. 38 minutes, not 30 minutes. Okay. Too much commentary. Okay. All right. Anybody have a question about, so meanings of sine, cosine, and tangent? Where are these ratios, opposite and adjacent and hypotenuse, where they come from? Where they come from, again, is measuring lengths using the radius. Measuring lengths to points on the circle using the radius. So let's do an example. Okay, so a motorboat leaves the shore going 28 kilometers per hour in a circular arc with a radius of 60 meters. How fast is the boat's distance from the shore changing when the boat has traveled a distance of 150 meters around the circle? Okay, so the challenge about these related race problems is the context continually, it's always different, right? So you've got problems about kites and rectangles and now a boat driving in a circle, and so they're all different, right? So we have to have something to hold on to that's a strategy that we're going to use that's always the same. And that's what I was trying to emphasize on Tuesday. So what is that overall strategy for these problems that's always going to be the same? Find what? Find an equation that relates the values, and then?
Identify the radius.
Okay, so this is the ballpark. This is what we're doing. This is the big pick, the structure of our solutions. We got to get an equation that relates the important quantities. You can think of this as like the accumulation part, right? It's just we got more than one thing accumulating at once, and we're finding the relationship of those accumulating quantities. Okay? Before we just focused on one thing that was accumulating, and it's one rate of change. Now we have more than one thing accumulating at once, and we got them changing at different rates at the same time. So you can think of this first thing as an equation that brings together our accumulating quantities, and then we're going to find the equation that brings together the associated rates. Okay, so how do we get this? So here's what I recommend. In order to figure out what the quantities equation is, here's the startup. Identify all the rates that they're talking about in the problem. Identify all the rates that they're talking about in the problem, and then based on that, assign notation and variables for all the quantities and rates. So x, y, z, s, r, dx dt, dr dt, dA dt. Okay? And then once you've got all your notation assigned, you know what rates are involved, then we're going to write the equation that brings together the accumulating quantities, and then we're going to take the derivative and get the equation that relates the rates of change. Okay, so let's identify the rates involved here. So a motorboat leaves the shore going 28 kilometers per hour. Is it a rate?
Yes.
Okay, there's a rate. So speed of the boat. And we know what that speed is, 28 kilometers per hour. Okay? How fast is the boat's distance from shore changing when the boat has traveled a distance of 150 meters around the circle? What's the other rate mentioned here? How fast is the boat's distance from shore changing? Is that a rate?
Yes.
Yes. So it's the rate which the boat's distance from shore is changing. Or we should say rate of the boat's distance from shore. Okay. Are there any other rates mentioned? That's it. We got how fast the boat is going, and then the rate of the boat's distance from shore. Okay, so now we need to assign variables for our quantities and our rates of change. So what are the relevant quantities here? Okay, the radius. And is that a constant quantity or changing quantity?
Constant.
Constant. So r is always 60. So let's draw that on here. So maybe the center is something like this. So this is 60 meters here, out to the boat's starting point. And it's 60 meters always, right, to every point where the boat is. That he's going in a circle like this, okay? So if we want, we could label that as 62. And that one is 60. Okay, what other quantities do we have?
We have the distance from the start to the finish.
The distance from the start to the finish. So
150 meters, yeah.
is that from here to here?
Yes. No, it's traveling along the circular path.
Okay, so the distance the boat has traveled along the circular path is going to be important, right? So that's like arc length. So you can call that whatever you want. Often arc length is S. So we'll use S because that's kind of conventional, but S is just a symbol. You can use your own symbol, right? So S is going to be the distance traveled by the boat.
Which is a constant.
Is that constant?
No.
It's not it's stopped at that point. So
Is it stopped at that point?
how I put it, I can understand that.
No, it's just we're pausing time, but that's continually increasing quantity. S starts at 0, and so yeah, we're interested in this moment of time, but time doesn't stop, right? So that distance is increasing. What other quantities? What else do we need? What other quantities do we need here? What's that? Yeah, so it's saying how fast is the boat's distance from shore. The boat's distance from shore, and we want to know how fast that's changing, so we're going to need to identify that distance from shore. So let's call it y, because it's kind of like a y coordinate, right? It's kind of like a vertical distance. So y is the boat's distance from shore. Any other relevant quantities? Yeah?
I'm not sure this is relevant, but because 60 is the radius,
Yeah?
you can't go more than one radius length. It seems the boat's maximum distance from shore is 60 meters.
No, the distance would be like the straight vertical distance. Like here the distance from shore is 0. And here the distance from shore is 60.
Yeah, that's
And
what
so now this is going to be less than 60.
Right, that 60 is the maximum.
60 is the maximum, that's right. Yeah. Right now it's closer than 60.
Right.
Okay, any other quantities that might be helpful here? Okay, well, what about rates? Okay, so we have the speed of the boat and the rate of the boat's distance from the shore. How can we use symbols now that we've got these quantities r, s, and y? How can we use symbols to represent these rates? So the speed of the boat. Can we symbolize that with our notation that we've learned? Some people are saying d what? ds dt. Isn't that ds dt? Because the distance traveled by the boat, how fast that's changing is the speed of the boat. So his rate around the arc, ds dt, is that 28 kilometers per hour. All right, what about the rate of the boat's distance from shore? dr dt? That's dy dt, because the distance from shore is y, so the rate of change of that is dy dt. Everyone tracking? Does it make sense? Okay, so now we need an equation so now we're ready for this. So we've got r is 60, s is the distance traveled by the boat, y is the boat's distance from shore. ds dt is that rate of change of that arc length, or the speed, 28 kilometers per hour. And dy dt is how fast that distance from shore is changing. Okay, so now we're ready to actually build our quantities equation. So, have you learned anything today in class in our Trig crash course? Can you write the quantities equation? See if you can do it. Quantities, not rates. There's no rates involved here. We're bringing together these quantities, R, S, and Y. Can you do it? No rates yet. No rates yet. What equation brings together our pertinent quantities? Go. See if you can do it. Okay, here's your hint if you're not making progress. 2 ways to represent that vertical distance in terms of the radius. 2 ways to represent that vertical distance in terms of the radius will give you an equation. 2 ways to represent the vertical distance in terms of, or measured by the radius. Okay, what's one way to do it? What's one way to write this distance relative to the radius? How can you write the relative size of this distance relative to the radius? Y over 60, or y over r. Let's just do y over r. Okay, now we want to write that a different way. How can we write the relative size of that vertical distance? Sine of theta. Okay, but what's that? What is theta? How can we write theta? What is the angle? The angle is the relative size of the arc length to the radius, right? That's what we talked about. The angle measure is the relative size of the arc length to the radius. So sine of the relative size of the arc length, which is the distance traveled by the boat, to the radius. Anybody? S over R. Did you catch it? 2 ways to represent that vertical distance relative to the radius. Taking y divided by r, what is it? About 3/4, right? Estimate that value right now. About 3/4, right? About 3/4 of the radius. That's what the value of sine was, about 3/4. So, but it's sine acting on an angle, and that angle is the relative size of the arc length to the radius, which is S over R. Any questions? Doesn't make sense. Now, can we plug in R equals 60 at this point? Are we allowed to plug in R equals 60 at this point? And the answer to that is yes, if it always stays constant. Does it always stay constant? Yes, so we can. Are we allowed to plug in S equals 150 right now? No, S is changing. If you plug in 150 right now, then you're just assuming that the boat is anchored there. All right, and so then it's the rate of change of this distance y will be 0. So you can only plug in things that are constant until you get the rates equation. So you can plug in r, that's fine. So we can do y over 60 equals sine of s over 60. That's fine. But you can't plug in 150 for s. Why? Because s is a changing quantity. It has a rate of change that's not 0. So now we're ready to go. So we're going to take the rate of change of every term with respect to t. So what is the rate of change of y over 60 with respect to t? So it'd be like 1/60th times dy dt. So this is like 1/60th y, right? Let me rewrite it that way. Equals sine of at 1/60th s, if that helps, for taking the derivative. Okay, so the derivative of 1/60th y with respect to t will be our 1/60th times dy dt. And then what about sine? Derivative of sine. Cosine. Leave the inside the same, right? But then we have chain rule, right? Times the rate of change of the interior, which I normally have put first, right? So I normally started by doing that first. So this time I'm doing it second, right? So the rate of change of 1/60th s with respect to t is 1 over 60 ds dt. So here's our related quantities equation. Here's our related rates equation. And so now the rest is just getting the right numbers in the right place, solving for the thing that we want. What's our unknown that we're trying to solve for? dy dt. We want this. So if we want that, that means somehow in the problem we are able to get every other variable. So what is s? 150 ds dt? 28. Careful. So what's going on here? Why am I saying that? We got meters and kilometers. This happens often that those units don't agree. So we already have started using meters here with the radius, and we put 150 meters in. So all we have to do is make this one meters per hour. So 28,000. And now everything's in meters and hours. Okay, so when you use your calculator and you do cosine of 150 times 1/60th, you got to make sure your calculator's in radians. Okay, all this stuff about measuring angle using the arc length in radius lengths, that's radians. So make sure your calculator is set to radians, and you're going to solve for dy dt. So when you do cosine of this thing right here, you got to make sure your calculator has to be in radians to get the right value there. All right, so everyone got that written down? I'm going to go to graph. So I'll just write down the answer. Okay, so when we plug everything in and solve this, does anybody have a dy dt yet?
I have negative 22.432.
Negative.
22.43.
So was it 22430?
22432.
22432. Does someone else get that?
That's meters, but it's going to be kilometers.
Right.
Decimals.
Yeah. Other people got that? We good? Okay, so that is, what units is that?
Meters per hour.
Meters per hour, so
Kilometers.
we want to change to kilometers per hour, or negative, like he originally said, negative 22.43 kilometers. Does the negative make sense? Why does the negative make sense for this dy dt?
Toward the shore.
What's the quantity y doing? Decreasing. Why is the quantity y is decreasing at this point? So the rate of change is negative when the quantity is decreasing.
Where'd the 28,000 come from?
28 kilometers per hour changed to meters per hour.
Meters. Okay.
We need everything else was in meters, so we needed it to agree. Okay, learn the roadmap. If you need an anchor, if you need something that's the same about all of these, it's the roadmap over there. That's what's the same about all of these.